Okay, over to you, Simon.
Okay, thank you very much, Matt. Well, good afternoon, everyone. And I'm Simon Watts, visiting professor at UCL. And I want to talk to you about this work I did recently. It arose from a NATO study group investigating the detection of submarine masts using radar at high grazing angles. When we've gone hunting for submarine masts in the past, we've traditionally done this at very low grazing angles in order to minimize the clutter return, and usually with non-coherent processing. But moving to higher grazing angles results in reduced signal to clutter ratios, so the question arises whether better forms of detection might be devised to overcome essentially the increase in clutter return with no significant increase in target return. And although we're at higher grazing angle, we'll find also that the clutter statistics can still be very spiky, even at sort of medium grazing angles. So in order to investigate in a bit more detail whether, for example, we could do better with coherent processing, which is also now a lot more feasible than it was in the days when we first started building non-coherent high-performance radars back in the 1970s and 80s. But if we're going to design detection processing with coherent or non-coherent processing, we require a good understanding of the target characteristics as well as the sea clutter. So let me just get rid of that. So here we are. I'm going to talk today about, based on this paper that I've given. Basically, we'll look at the radar signatures of submarine masts and their wakes. And I don't know whether you can see, I don't know if things are blocking, but you can see on this is actually a Russian submarine, I think, but you can see what submarine mast. It's got a lot of masts up, but this is the attack periscope, the thing we're particularly interested in. Sorry, this is the attack periscope here. This is the search periscope. This is an ESM mast, and here's a comms mast. And this is the wake, which I'll be talking a lot about. We'll look at the available evidence for these masts and their wakes and measurements, which are not much in the open literature, but there is a bit. From that, I develop a simple model of the coherent signature of mast and its wake. I'll then just review the clutter models that we use for coherent processing, and then investigate the implications for the choice of target detection algorithm, either non-coherent integration with pulse-to-pulse frequency agility or coherent integration. With one of the variables I'll particularly look at will be the choice of data sampling frequency, essentially the pulse repetition frequency. Then there'll be some conclusions. So first we need to understand the characteristics of the radar returns from a submarine mast moving through the water. A submarine mast will always be in motion in order to fly the boat, but typically a maximum speed of about 6 knots or 3 meters a second when the mast is up, in order to minimize the wake, which could be visually seen as well as from a radar. So what we'll find is that there'll be a return from the mast itself and also the returns from its wake, which will have separate characteristics. And clearly, data from these sort of targets is very difficult to obtain, certainly in the open literature. But some measurements were published in 2012 by CSIR in South Africa. And I've given the reference down here, Anderson and co. here. And they used a wide bandwidth coherent radar to separate the mast returns from the sea clutter and then extract the mast radar cross-section. They don't give any absolute values of radar cross-section, but we can learn a lot from their paper about the statistics of the returns. And we couldn't get hold of the original data, but I redigitized the returns from their paper. So this is the paper, one of the figures from their paper, showing power in dBs against time, 35-second sequence for a mast. And this is the mast return here, and this is the clutter, and here is noise. So I redigitized the mast data. Here it is plotted over 35 seconds. This is intensity against time. You can see it's fluctuating quite a lot, even over this short time period. But I then looked at the amplitude statistics of the mast return intensity, essentially without any clutter or wake because of the Doppler filtering they did. And I fitted it to a gamma distribution. And we can see at the bottom of the page down here, a fit log, I call it PFA, the complementary, the CCDF of the target RCS with fits to a gamma. And this is gamma with a nu of 1, which is essentially an exponential distribution. And our data is very close to this. It has nu of about 9.9. Fit, and that's the actual data in blue, and the fit in orange here. So what we conclude from this simple extract is that what we often use in the model in the past for these mast returns is a simple swirling 1 or swirling 2 model with an exponential distribution of the radar cross-section. So swirling case 1, remember, is slow fading, and case 2, this is within a radar dwell, for example, and case 2 is fading from pulse to pulse. So that was the RCS measurement. In terms of absolute values, so old published data on RCS masts suggests a mean value of about 1 meter squared for an attack periscope. But also importantly, an exposure time probably as little as 5 seconds. So a submarine putting up its search periscope will put it up for 5, perhaps for 6 or 7 seconds, and then bring it down again. So we haven't got long to detect these targets, and they are very small. And this was old data. So, with modern non-hull penetrating masts and optoelectronic mast heads and so on, it's most likely that the radar cross-section could be even smaller than 1 meter squared mean, but fluctuating like this over a short time period. But also, over a longer time period, these mast returns fluctuate even more than that. So this is a plot taken from the same paper of a submarine showing its mast doing a complete 360-degree circuit. And they plotted over this the mean radar cross-section and the 90% values of the measurements they got, a number of measurements, and the 10% values. And here this is the original values in the paper. And what you can see is some quite systematic variation over time. It's not just a random fluctuation, but perhaps fluctuation over perhaps 20 dBs over time, with some apparent consistent differences at different look directions. And this could be due to all sorts of things like varying depth keeping, different radar cross sections of the mast from different aspect angles, waves coming over, and so on. But what it does show is that the returns will fluctuate, perhaps over 20 dBs with aspect angle, but also at any particular aspect angle. I fitted using the mean and 90% and then the mean and 10%, just fitted those again to a gamma distribution by matching the moments. And you get values of shape parameter which are of the order of one, some slightly lower than one, some slightly more than one. So where you're getting values slightly more than one, you get sort of these very, very high values of shape parameter are becoming more noise-like, and perhaps due to an incursion of wake or clutter returns into the measurement, but also some much more spiky values showing some less than one, perhaps due to variable depth keeping over the measurement interval and so on. So a complex scene, but the overall message is perhaps a swirling one model, but with the absolute radar cross-section fluctuating a lot over time. The return from the wake is also important. And what we've got here is a range Doppler plot of the returns taken from the CSIR paper. And you can see the mast here is quite separate. This is the clutter over sort of plus or minus 1 meter a second, not centered on 0. And then this block of returns here is the wake. So you can see that the target has quite a narrow spectrum, but the wake has a very broad spectrum spreading out over here, sort of plus or minus 3 meters a second. And the Doppler speed of the target is about 2.5 meters a second. So, as I mentioned before, submarine masts, exploding masts, typically don't travel faster than about 3 meters a second. And so their Doppler shift will often place them like this, well outside the Doppler spectrum, the clutter spectrum, sorry. But clearly that depends very much on the direction from which you're viewing the moving target. And a target with a speed of 3 meters a second could give a Doppler shift between plus or minus 3 meters a second over this interval here, with the wake shifting accordingly with it. And so in our example here, with a target velocity of 2.5 meters a second, we've got a wake spreading possibly over plus or minus 3 meters a second. And if you add up all the energy in the wake return spread over frequency, it's going to be, in this example, perhaps comparable, in fact, with the target power. So, armed with these simple observations, I proposed a simple model for a target with a wake. And so you've got a mast, which is our periscope, with a radar cross-section, which I called M. And this has a narrow Doppler spectrum and a narrow range extent, and a Doppler shift for a given speed dependent on the viewing direction. And the mean radar cross-section varying with exposure, viewing angle, and so on, but in all cases having a swirling case 1 characteristic. And then we've got the wake, which has got a broad spectrum. I've got it spread over a total bandwidth of B here. And this will be, we assume, will have more or less Gaussian amplitude statistics in much the way of the clutter spectrum returns within a given bin. And the mean total radar cross-section for all the returns in the wake, I've assumed will be constant for a given mass speed. And then we've got the total return, then our target, which we actually want to detect, is actually the mass return plus the wake return. And because these two will be fluctuating, we've got a mass to wake ratio, which I use to characterize the variation, the balance between the two, if you like. So when the mass to wake ratio is 0, the target return is dominated by the wake, so nearly all wake, but with the mass-to-wake ratio of infinity, the return is dominated by the mass, and the weight contribution is insignificant. So and just actually, I'll just go back one. This will have this mass, I've assumed, will have a swirling case 1 target. This wake will also have Gaussian statistics, and I'm assuming that this is more range extensive. So, for example, if we use pulse-to-pulse frequency agility, that might well have a swirling case 2 characteristic for non-coherent processing. If we change the radar frequency by at least the pulse bandwidth from pulse to pulse, that should decorrelate returns which are spatially uniformly spread over the range interval, the range resolution interval. So as well as a target model, we're going to need a coherent clutter model. And the clutter itself is a complex target. We see here an old picture, C state 2. This is the time history of C clutter of Doppler spectra from a single range cell. This is 32 seconds, and the radar was sampling at 1 kilohertz, and you've got a Doppler spectrum, unambiguous Doppler spectrum between plus or minus 500 hertz. The X band, but you can see over time that the spectrum, well, the spectrum isn't centered on 0, it's asymmetric, but also its width is fluctuating quite considerably over time, over a few seconds. This is sort of breathing, and these large excursions here, for example, might be due to a breaking wave or to wind blowing spray off the top of the wave, something like that. But if we're going to model the clutter spectrum, we've got to somehow capture this time evolving, and you get a similar behavior in range, a range evolving characteristic. And I'm not going to go through the derivation of this model, but it's in the literature and in my books and so on. This is the evolving Doppler spectrum model. And here we've got clutter, which is often shows this strong spatial correlation due to waves, wave patterns, for example. So we've got a fluctuating intensity, which may have a gamma distribution if we're going to use the K distribution model for C clutter. So you've got an intensity, which is modeled by a gamma distribution, which is given by this PDF here, which I can probably use a laser pointer. This probability density function for the clutter intensity. And we found that we could model at any particular instant, at any particular range, we'll have the spectrum will be reasonably well modeled by a Gaussian-shaped power spectral density, shown in dotted lines here. And here are 2 examples from a data set, actually a CSIR data set, showing at any instant you've got this spectrum, which is actually quite well fitted to a Gaussian shape. But in these 2 different examples from different parts, a high intensity part and a low intensity part, the shapes are Gaussian, but the widths are different. And also the mean Doppler shift is different for these 2 examples. And so we have an evolving model where we have a mean Doppler, which varies with intensity, and a spectrum width, a standard deviation of a Gaussian shape, which also fluctuates with some probability density function. And we found we could model the mean Doppler by this simple expression that is simply a constant value plus some offset, which is a function of the mean Doppler the intensity at that point. That gives you the overall mean. So it's A plus B times the intensity of the clutter. And the spectrum width, I modeled it simply as a normal probability density function with a mean and a standard deviation. And models like this are wonderful, but they're no good unless you can actually put values on these values for mean, standard deviation, A and B, and so on. But again, there are a number of papers published by myself and Luke Rosenberg and others in DST group in Australia, modeling a wide range of different clutter conditions, fitting these parameters to different weather and sea conditions. So armed with this model, we can actually look into any particular Doppler bin. We can work out the first and second moments of clutter intensity, assuming an idealized filter with a passband delta F for our Doppler bin and a center frequency FD, the Doppler frequency. And so looking at the clutter over range, if I go back here, if I look at or range or time, if I look at over this interval going up here, I can get an average mean and standard deviation of the clutter using my model, and then using the mean and standard deviation, I can fit that to a gamma distribution in the clutter. We found that the statistics of the clutter in individual Doppler bins was actually quite well represented by K distribution, so with a gamma distributed intensity. We can also write down expressions for the clutter to noise ratio and for the noise power in each Doppler bin, following on from Doppler filtering. So so we now have a knowledge of the statistics in our coherent model of the amplitudes, the probability density function, and the clutter to noise ratio. And from that, we can then start to calculate probabilities of detection and false alarm when we set a threshold. So first of all, we looked at some detection schemes. First of all, non-coherent integration. And the aim here is to investigate the effect of the mass-to-wake ratio on different detection strategies for a target in C clutter. And so I'm going to use pulse-to-pulse frequency agility. I'm assuming that the mass is still actually restricted in range, so this will still have a swirling 1 characteristic. The clutter speckle and the wake will be decorrelated from pulse to pulse and have swirling 2 characteristics essentially. We know what our clutter noise ratio is. We know what the K distribution shape parameter is. We know what the noise is. We use the K plus noise model. And we can calculate the signal to interference ratio, the signal to clutter plus noise, required for a given PD and PFA for different values of mass to wake ratio. And then for coherent integration, I'm just using here just a simple post-FFT detector. Again, the mass seems to be swirling 1, a wake bandwidth B, and our clutter noise ratio and shape parameter determined in each Doppler bin, centered on some frequency F here, using our evolving Doppler spectrum model. And then we can vary the pulse repetition frequency and the mass to wake ratio and calculate the signal to interference ratio required for a given PD and PFA in each Doppler bin. So first of all, non-coherent integration. We've got our clutter parameters. I've used a modeled example, which is spelled out in more detail in the paper, but I've just looked at an aircraft flying at 20,000 feet, looking at 20 miles range And for the particular situation we've modeled, we've got a cluttered noise ratio and a K-distribution shape parameter in the time domain data. And we're going to integrate 16 pulses using pulse-to-pulse frequency agility. And I've set the PFA at 10 to the minus 5. And with 16 pulses, this is the plot of signal to interference ratio against PD for different values of mass-to-weight ratio. So we've got mass-to-weight ratio of minus 20 dBs. So this is essentially all wake, and this sort of curve here is the essentially a swirling case 2 detection curve. But as the mass-to-weight ratio increases, we end up with essentially a swirling 1 target with 30 dBs when you've just got the mass and no wake, and so we get a characteristic like this, which is pure swirling 1 detection. And then in between, you get some intermediate values for different values of the mass-to-weight ratio. And just yes, so and so we can see that, and you remember we said that our target would only have an exposure time of perhaps 5 seconds or something. So we can't be operating with sort of low values of PD, half or something like that. We're going to have to operate with values of PD, looking for this sort of target of 0.9 or so. And you can see now that at these high values of PD, the mass-to-weight ratio has a very significant effect on the detectability of a target, or the signal interference ratio required in order to detect the target. So that's a very significant variation, 10, 15 dBs over the full span of mass-to-weight ratio. We can also look at what happens when we vary the number of pulses integrated. So I've got, this was n of 16 here, but this is plots for 32, 16, and 8. For mass-to-weight ratio of minus 20, this is the swirling 2, and this is the swirling 1 case. And you can see that for the swirling 1 case, the number of pulses integrated has actually very little effect at high values of PD, but a much more significant effect for the very low mass-to-weight ratio. And we can do similar things with coherent integration. And I've got n equals 16, and I've plotted here the cluttered noise ratio and the shape parameter as a function of Doppler frequency, averaged over local range bins using the evolving spectrum model. But now I've also looked at different values of pulse repetition frequency. And the previous example was for pulse repetition frequency of 1800 hertz. And here this is plot D. Here we can see this is cluttered noise ratio as a function of Doppler frequency, normalized Doppler frequency here. And this is the shape parameter. So we get some very low values of shape parameter in the edges of the spectrum, where we see the spectrum intermittently, sorry, and higher values near the center. But as we reduce the pulse repetition frequency, we see that these start to spread, but ultimately they will alias. And if we get a very low pulse repetition frequency, just say 100 hertz, then this is plot A and A here. In this case, the clutter is totally whitened over the spectrum, over the unambiguous Doppler spectrum. And so the clutter is just spread out uniformly like this. And this actually can be quite advantageous if you're only trying to detect targets within the clutter spectrum. Now, obviously, a PRF of 100 hertz is not very practical as such. The update rate would be far too slow. But there's much more discussion in the paper. But there are methods in the literature for achieving very low sample rates while maintaining a high update rate using mechanically scanned, electronically scanned antennas. An antenna with electronically scanning, but also mechanically scanning, which is continually looking back at 100 hertz rates at different spots as it scans around mechanically. So there are ways of achieving this without just simply reducing your update rate. But the important thing to notice is what happens here. Here you can see with a 500 hertz, the clutter is not uniform over the Doppler width, but it's getting quite spread out. And then by the time we've got to 100 hertz, it's essentially constant amplitude over the unambiguous Doppler regime. And this value of cluttered noise ratio and this value of shape parameter are just exactly the same as the ones in the time domain data. But now, if we're going to Doppler filter, so we're going to start filtering, putting Doppler bins which will sample the clutter spectrum, and we'll get a variation of shape parameter across in frequency. But also now, if our wake has a significant bandwidth, if we filter with too fine a Doppler filter, then we will lose energy from the wake in a particular Doppler bin, because the Doppler bin width will be narrower than the total width of the wake. So whereas our non-coherent detection, we got all the energy from the target and the wake, we assumed they were all within the range resolution cell. But now, if we're going to do Doppler filtering, we may find we end up losing energy from the wake as we filter. And what we find is the total target energy in a Doppler bin containing the masked return will be M, the masked RCS, plus some fraction beta of the total wake RCS. And I've given examples for different values of beta, depending on the value of the pulse repetition frequency, FR, relative to the number of pulses in the FFT interval and the bandwidth. And so beta may be 1 if we've got a very coarse Doppler, and it could be 1 over n. So we only get where n is the number of pulses in the FFT if our pulse repetition frequency is very much less than the bandwidth. Again, lots more detail in the paper if you want to go through it in detail. So now I've plotted some results. This is for a particular example, a particular range that we looked at before, 20 miles. And I've now plotted the minimum detectable radar cross section as a function of Doppler frequency. The function of Doppler frequency, minimum detectable radar cross section for different values of mass to wake ratio. And this is for PRF of 1800 hertz. And the PFA in an individual Doppler bin will now be a factor n lower, because we're going to collapse all the Doppler bins in order to declare a detection, to give us an overall PFA of 10 to minus 5. You can see here these different target detectabilities. Obviously, you need a much bigger target near the center of the spectrum here. If the target had a very high Doppler shift, putting it out here somewhere, then clearly coherent processing has a big benefit. And you can see that there will be no no discussion as to which was best. It would be much better to use coherent processing once you're outside the clutter, the exo-clutter region. But within the clutter, the endo-clutter region, these dotted lines here show that the equivalent non-coherent detection using coherent integration with pulse-to-pulse frequency agility. And these are the plots for the mass to weight ratio of 30 dBs down to minus 20 dBs with the equivalent colors to the Doppler. And I've replotted that here over an interval of plus or minus 200 hertz, which is the velocity of our target mass, which is assumed to be restricted to be within this region. You can see now that actually for a significant part of this spectrum, non-coherent processing is going to give you a lower minimum detectable radar cross-section than coherent processing. And as you start to go outside the spectrum, then the coherent processing starts to win. But the interesting result is that non-coherent integration performs better over much of this Doppler frequency range, especially for very low values of mass to weight ratio. I just put something in the paper looking at the difference between a long track and a cross track direction. So the previous example was looking a long track, so I could ignore any spreading of the clutter spectrum due to the finite antenna beam width. But when you look at cross track, then you get a platform motion effect, which will spread the clutter. What we can see here are the dotted. This is the solid lines are the long track results, and the dotted lines are the cross track results. And what you find is that normally people try and avoid or mitigate the effects of cross track Doppler spreading. But if you know you're going to be detecting within the clutter spectrum, it actually gives you some benefit because it spreads the clutter out more uniformly across the Doppler bins. And so it gives you a better performance, these dotted lines here near the center of the spectrum. It obviously makes it worse near the edges of the spectrum because you're now increasing the clutter out in these regions. But again, we're still getting a potential benefit even with a high mass to weight ratio of non-coherent processing. We can also look at the effect of varying the number of pulses in our FFT. I've now plotted different examples for different mass to weight ratios and for n equals 8 and n equals 32. And the previous example was for n equals 16. And the red lines here show a mass to weight ratio minus 20 dBs. And it can be seen here that if we increase the number of pulses integrated, it actually reduces performance because less wake energy appears in an individual Doppler bin. The blue lines show mass to weight ratio of plus 30 dBs here. And now an increase in N provides an improvement in performance as you would normally expect. And for non-coherent processing, increasing the number of pulses always increases performance. So the dotted lines show that the higher number of pulses here. So all this is sort of adding up to show that it's a complicated situation, and you need very good models of your target and your clutter to work out actually what is the best strategy for a particular situation. The other thing that I mentioned earlier on was the effect of reducing the pulse repetition frequency. So increasing the sampling interval. And I've modeled that here simply as a reduction in PRF. But the underlying assumption is that the mass has a narrow Doppler spectrum, so its spectrum is not spread significantly by reducing the PRF. but the wake and the clutter will become alias if the sampling interval is too great and spread over the unambiguous Doppler space. And as I mentioned, although PRF is impractical for a surveillance radar, but there are references in the paper to using a mechanically scanned E-scanned antenna to using look back as you scan around in azimuth to build up returns at lower sampling rates at different bearings. And as we mentioned before, as the PRF is reduced, the clutter and wake energy will eventually be uniformly spread over the n Doppler bins, with the mass return still in one Doppler bin. And so I just got some plots here of the effects of reducing PRF. So this is for PRF of, actually the heading here is, it says 500 and 1,000, but actually I've got the plot here is for 1,000 and 1,800 hertz, and then for 500 and 100 at the bottom here. And again, this is master wake ratio of -20, master wake ratio of 30, and you can see that from a master wake ratio of -20 dBs here, where the wake is dominant, value of sorry, I'm skipping on a slide. Yes, the value of PRF has very little difference, but as we go down to go up to a higher master wake ratio, then the different PRFs start to have a significant effect. And here you can see the effect of aliasing over when you've got 100 hertz, you've just got these uniform probability detection with Doppler, but again, in some circumstances, you're still going to get better performance with non-coherent processing. So down here with 100 hertz, non-coherent is still better when the master ratio is less than about 3 dBs, but the coherent will be better when the master ratio is greater than about 4 dBs. And so on. So depending on your PRF and the underlying assumptions, coherent or non-coherent will be better under different circumstances. So if the sampling rate is sufficiently low, so the clutter and wake spectra are fully whitened, then it's quite easy to investigate the effect of changing FFT length on different values of master wake ratio. And you can see that with a master wake ratio of -20 dB, so the wake is dominant, the value of N has no effect on performance at all. Oops, sorry. These are for all these plots lie on top of each other, because what happens is that as you get an increased integration gain by increasing N, that's counteracted by an equal reduction in wake energy in the Doppler bin. But obviously, as the master wake ratio gets larger, then we get comparable increases with a very high master wake ratio. You get the maximum increase with N, and similarly with intermediate values here. So this is just a very quick sort of skim over some of the issues, but the take-home message, I think, is that the best detection strategy is going to be very dependent on the amplitude statistics and Doppler spectra of the target and the clutter. And you need to also take into very careful consideration the dwell time available, the update rate you need, the pulse bandwidth you can manage, and so on. If you're going to use non-coherent detection, you really want the range resolution to allow capture of the wake signature to get the most benefit. And you need to be able to use pulse-to-pulse frequency agility to decorrelate the wake and the clutter returns. If you're going to use coherent processing, then it's worth noting that you might think of using a wider bandwidth, but this can lead to range walk problems. It's a traditional problem with Doppler processing. You want to dwell over a long period, especially at very low PRFs, you're going to walk from one range bin to another if you're not careful, and then you have to correct for that. And so it may be better to use shorter coherent dwells and then you could change frequency from dwell to dwell and use get pulse to pulse or burst to burst frequency agility, get a benefit from that. And in all these examples, scan to scan integration will improve clutter decorrelation, but you're then going to have to account for range walk in the target, which will be moving. And we talked about aliasing the clutter spectra, which can give significant performance gains. But you've got to think very carefully about what's going on here. So if I've got a sampling rate with 100 hertz and I'm collecting 16 pulses, that implies a dwell time of 1.6 seconds. And that's a very long time in radar. So over that period, the clutter texture may partially decorrelate, and it may not be possible to ignore range walk. And the mass intensity may also change over this time, so it may not be appropriate to ignore the finite spectrum width of the mass component over long dwell periods. So again, shorter coherent bursts and then non-coherent integration, possibly allowing for range walk. And lastly, ideally, what we want is a dynamic target radar cross-section model with characteristics which are correlated with the instantaneous sea surface, because obviously you've got a wave pattern going over, the exposure of the mass will vary, but this will be correlated with the sea surface. And we also need to be able to model the dynamics of the boat, submarine, which will be flying and sort of porpoising and varying exposure as it flies as well. So for slow-moving targets, simple coherent detection may not perform as well as non-coherent detection with pulse-to-pulse frequency agility. And when the target comprises a discrete target with a narrow Doppler spectrum, combined with a wake having a broad spectrum, the relative benefits of coherent and non-coherent processing are just more complex and need to be looked at very carefully. And this paper doesn't give the answers to all this. It's just, I hope, highlights some of the features that need to be considered when designing a detector, and give something to go on when more data from real targets, if and when that becomes available. So there we are. That's the talk. These are the papers. That was the original. So this is the original radar conference paper, and this is an extended version which I was asked to do for the RSN, which is now out as Matt has circulated. So that's it. Thank you very much.